Hey, welcome back to chemistry. You're here with Mrs. Mays, and today we're going to use redox reactions to make batteries. Hold on, it's going to be a bumpy ride. Electrochemical cells is our starting place. You see, electrochemistry is where we can describe the relationship between electricity and chemical reactions. And I need a better color because black is not going to work. Specifically, the type of reaction we're looking at is a redox reaction. Electricity is simply the movement of electrons, and if we can get electrons to move from one substance to another, we could harness that power and make electricity. So energy that's released in a spontaneous redox reaction and is used to perform electrical work, we call that a voltaic cell. Where did my pen go? So when energy is released in a spontaneous redox reaction and then used to perform electrical work, we call that a voltaic cell, or they'll be called galvanic cells. It means the same thing. It means the reaction is spontaneous and we didn't have to do anything to make it happen. It just happens all on its own. The electrons that are flowing from one substance to another transfer through an external pathway rather than directly between reactants. Usually we use a wire to move the electrons along. It's a pretty efficient system. And when we have this reaction taking place, the metals that we use in the circuit are called electrodes. So to build a battery, you've got to have electrodes and a pathway for your electrons, and there's a couple of other things we've got to have too. Let's take a look at it.
A galvanic cell is a spontaneous electrochemical cell in which electricity is produced by means of a spontaneous redox reaction. In this cell, zinc metal will be oxidized and copper 2+ ions will be reduced. To complete the electric circuit, the solutions must be connected by a conducting medium through which the cations and anions can move. This requirement is satisfied by a salt bridge, which in its simplest form is an inverted U-tube containing an inert electrolyte, such as sodium nitrate or potassium chloride, whose ions will not react with other ions in solution or with the electrodes. At the zinc electrode, zinc metal is oxidized, losing 2 electrons to produce zinc 2+ ions. At the copper electrode, copper 2+ ions are reduced, gaining 2 electrons to produce copper metal. Electrons flow from the zinc electrode to the copper electrode. The zinc electrode is dissolving to zinc 2+ ions over time, and copper metal is building up on the copper electrode. Click on one of the buttons to view that portion of the galvanic cell on a microscopic scale. At the zinc electrode, zinc atoms are losing 2 electrons, forming zinc 2+ ions, which enter the solution. The 2 electrons lost by zinc metal flow through the wire to the copper electrode. Note that only zinc 2+ ions are shown in solution. Other ions and water molecules are not shown to focus on the oxidation of zinc metal to zinc 2+. Electrons formed at the zinc electrode travel to the copper electrode. 2 electrons combine with each copper 2+ ion in solution to produce copper metal. Note that only copper 2+ ions are shown in solution. Other ions and water molecules are not shown to focus on the reduction of copper 2+ to copper metal. The salt bridge contains sodium nitrate, which exists as sodium ions and nitrate ions in solution. As the zinc electrode is oxidized to zinc 2+, a positive charge builds in the solution due to the zinc 2+ ions. If this positive charge were not counterbalanced, the galvanic cell would cease to function in a short period of time. The negative nitrate ions flow into the solution containing the zinc electrode, and the positive zinc 2+ ions move in the opposite direction to balance the charge. For this cell, nitrate ions are chosen because they do not react with other ions in solution or with the electrode. The salt bridge contains sodium nitrate, which exists as sodium ions and nitrate ions in solution. As copper ions in solution are reduced to copper metal, positive ions are removed and a negative charge builds up in the solution. If this negative charge were not counterbalanced, the galvanic cell would cease to function in a short period of time. The positive sodium and positive zinc 2+ ions flow into the solution containing the copper electrode, and the negative nitrate ions move in the opposite direction to balance the charge. For this cell, sodium ions are chosen because they do not react with other ions in solution or with the electrode.
So batteries basically consist of two electrodes, an anode and a cathode, a place where reduction occurs and a place where oxidation takes place. The electrons that flow from one element to the other flow through the wire, and the voltmeter is measuring how much voltage is generated as the electrons flow. So let's review. The anode is the electrode at which oxidation, or the loss of electrons, occurs. The cathode is the electrode at which the gain of electron occurs. So that's called reduction. Right? Gain of electron is reduction. The salt bridge is what connected the two half cells together and allowed for the flow of ions between the two half cells to balance out those charges. As the electrons leave, we have to put negative charges in place of the electrons, or it would short circuit our battery. The salt bridge is carefully chosen. The solution has to not form a precipitate with any other ion in that solution. So we choose spectator ions like alkali metals and nitrates, chlorates, acetates, the types of things that don't react with other ions. Then the salt anions migrate toward the anode, and the salt's cations migrate toward the cathode. The electrons then flow through the wire from the anode to the cathode. And to remember the direction that the electrons move, we use this mnemonic device, fat cat. Do you have a fat cat at your house? I have a fat cat at my house. So that means electrons flow from the anode to the cathode. Fat cat. I have other animal analogies for you as well. So think about anodes and anodes is where oxidation occurs. So there's an ox, and then reduction is at the cathode. So in addition to our ox, we also have a red cat. An ox, a red cat, and a fat cat. Old McDonald's farm is looking pretty strange. An ox, a red cat, and a fat cat. An ox, anode, oxidation. Red cat, reduction is at the cathode. And then fat cat, because the electrons flow from the anode to the cathode. Pretty weird looking old McDonald's farm. So to calculate the standard cell potential, we can determine which metal will be our best cathode and which metal will be the best anode, so that we can get a spontaneous reaction. Remember, a spontaneous reaction is one where it just happens all on its own, and that's what you want for a battery. If you have to add energy to make it go, then your battery is not very good. We want something that's just going to generate energy all by itself. We call this energy that's generated the electromotive force, the energy that's making the electrons move. And it's caused because there's a difference in potential energy between the different electrodes. Like if a swing is at the top of its swing, then the potential energy difference makes it fall back down to the ground. This force allows the electrons to be pushed along the wire, and we call it E cell, the cell potential, and it's measured in volts. So when I ask you to calculate the cell potential, that means we're basically talking about how much is that EMF, how much are we pushing electrons through that wire. The more we can push electrons through, the more electricity it generates. So cell potential is going to be positive for spontaneous reactions. It would be negative if you had a non-spontaneous reaction. And in that case, you would have to add electricity to get that reaction to go. And that's not what we want when we're trying to build a battery. The cell potential is based on standard reduction potentials of each electrode. So we have to know how much energy would there be to reduce one of those elements compared to the other element. So the potential associated with each electrode basically is describing the ability for the reduction to occur at the electrode. Some substances are easier to reduce than others. In other words, we can add electrons to the electron shells of certain elements a lot easier than other elements. We always compare the metal to a standard hydrogen electrode, or hydrogen gas, basically. We measure what's hydrogen gas and we call that 0, and everything else is going to be something either higher than hydrogen for its reduction potential or less than hydrogen's reduction potential. So you'll find a chart like this in your honors chemistry handout to summarize the reduction potentials for most of the electrodes you're working with. If you come across an electrode that is not shown on this page, just ask me and I'll help you find its potential. So let's calculate the cell potential. Here's what we do. We take the reduction potential from this chart for the cathode minus the reduction potential for the anode. How do we know which one is the cathode? It's the one that's most positive, because that means it's easiest to reduce. And then the anode is the one that's more negative. So the more positive the reduction potential for a metal, the greater its ability for reduction will be. That's the one that we want to use as our cathode in our battery. And the metal that has a positive, what is this? I keep saying the same thing over and over. Got it. Thus, the metal that has a larger reduction potential is going to be our better cathode in a voltaic cell or galvanic cell. For example, let's look at the reaction between cadmium and tin. How do we decide which one is going to be the cathode and which one will be the anode? We want it to be spontaneous, so we need a positive voltage. So I'm going to compare their reduction potentials on my chart. So in the yellow, you'll see the cadmium. For cadmium to add 2 electrons gives us a cell potential, produces, oh my gosh. The reduction potential for cadmium-2 is negative 0.40 volts. And for tin in green, why is that white? Okay, weird. For tin, the reduction potential for tin-2 is a negative 0.14 volts. So which one is more positive? Cadmium or tin? Well, they're both negative, right? But which one is more positive? Right, tin. So let's use tin as the cathode because it's closer to being positive than the cadmium. We'll let the cadmium be our anode in our battery. Then we'll get a spontaneous reaction. So we calculate the cell potential by taking the potential for the cathode minus the potential for the anode. So that would be a negative 0.14 volts minus a negative 0.40 volts. And now I need my calculator. So I had negative 0.14 minus a negative 0.40. That gives us a cell potential of 0.26 volts, positive 0.26 volts overall. And since this is a positive value, we see that the cell potential is indeed spontaneous for our battery to work. That's good. We want to produce energy, not use it up. Batteries that use up energy are no good. Let's try another one. And this one is a little bit trickier because now I have to decide which reactions are which. What's our half reactions? So let's go back to the lesson we just did about balancing complex redox reactions. First of all, I have lead 4 oxide turning into lead 2 ions. That's one of my reactions. The other reaction shows sodium metal turning into sodium ions. And remember, sodium metal has 0 charge. So my half reaction shows what's actually taking place, and we're not sure if it's spontaneous or not, but we're going to have to go with this. If sodium is a 0 to a +1, because that's what my reaction says, that means I've lost 1 electron. That's going to go, because the charge went up, right? It's oxidized. So I write my electron as a product. And for lead to go from a +4 to a +2, that charge is going down. It's being reduced. My lead has to gain 2 electrons in order for that reaction to take place. Now let's balance our oxygen by adding water. I need 2 waters. And I have to balance my hydrogen on the other side by adding how many hydrogen ions? 2 waters means 4 of those. Boy, I don't have a lot of room to write that. Okay, so 4 hydrogen ions on the other side. So there's my half reactions, and I need to look up the cell potential. For sodium, it's a negative 2.71 volts. So let me write that down, negative 2.71 volts. And then for the lead 4 reaction to lead 2, that's positive 1.46. Well, at least this one's easier to decide which one should be the cathode, right? The more positive of the 2 electrodes is certainly the one with lead. So let's use this reaction for our cathode, and the anode will be the sodium. Of course we knew that, right? Reduction happens at the cathode and oxidation happens at the anode. Anox and red cats. Crazy old McDonald's farm, right? Okay, so my cell potential is calculated by subtracting the potential of the cathode minus the potential of the anode. Let's put our values in. 1.46 volts minus a negative 2.71 volts. This is going to give me quite a lot of energy, isn't it? Look at this. Calculator time. So I have 1.46 minus a negative 2.71 volts. That gives us 4.17 volts overall. I knew that would be a big positive number compared to the other ones we had. 4.17? Yeah, 4.17 volts overall for that particular electrochemical cell. That's a lot of energy, and we can harness that energy in a battery. So this is what we use redox reactions for. It's one important application. Of course, there's other important applications like electroplating and electrolysis, which would be the non-spontaneous reactions. But in honors chemistry, for now, this is what you're responsible for: calculating the cell potential for a battery and identifying the anode and the cathode using the half reactions. Keep practicing, and I'll be in class to help you.